So imagine a cyclist. Um, this is a reasonable amount of power for a cyclist of this mass to be able to produce for a long time. So several hours. You can get 120 watts out of a person. Highly trained people, maybe more than that. So if she's riding at 12 meters per second, um, there's a frictional force on her. The main drag force is air friction. So how big is that? I'm going to open up multiple choice polling here. Let's see. So you can now tell me what you think the answer is. Remember, our idea is that power is dot product of force with velocity. Now, Jacob, you can click on that rather than typing. It's all good, Jacob. Um, but he is right. Again, I'm going a little bit fast here just because of the interest of time. So I know that the total power is the power she's putting into the pedals plus the power from drag. And we know that the work being done on the pedals is positive, and the work being done by drag is negative. But I also know that the net power being applied to the bicycle is 0 because it's going at a constant speed. 12 meters per second is the sustained speed. So that tells me that the power on the pedals is minus the power from drag, which is minus the force of drag times the velocity. So this minus sign is that one, and that minus sign comes from the dot product, since the force of drag is opposite the velocity. Why is it 10? Well, let's solve for that. So canceling my minus signs, this tells me that the power applied to the pedals is F drag divided by velocity. Oops, times velocity. I'm getting ahead of myself. So F drag is the maximum power I can pedal with divided by the velocity that propels me. So that's giving me 120 watts divided by 12 meters per second. Does that help, Grace? Okay. I want to do one more example now. Now I'm imagining our same cyclist going up a hill. So let's compare this. The maximum on flat ground was 12 meters per second. My girlfriend is a pretty active cyclist, and these values are basically, like I checked with her, these are the real values for, a person like her. Um, so if I want to know how fast I can go up a hill, so now we're ignoring air drag because we're going so much slower, and now the thing holding us back is gravity. So now I've got the power from the pedals plus the power from gravity equals 0. Again, the power from the pedals I know is 120 watts. the power applied by gravity is going to be, again, the force of gravity dot velocity. So if I think about these vectors, if I'm going up a hill, there's gravity, there's the velocity. Notice that they are, not parallel. If I then look at the vertical component of velocity, so this is going to be mg times minus vy, again using the definition of the dot product as force times the component of velocity in the direction of that force. This is going to give me minus mg v sine theta. Since looking at this, Vy is V sine theta. Why negative? Because gravity goes down, right? So I want the component of the velocity in the direction of force, and force is in the minus y direction. So this means that the power from the pedals is going to be minus the power of gravity from here, and this gives me, I'll run 20 seconds over, I'm sorry. Power of the pedals is mgv sine theta. When you do the math, the maximum velocity comes out closer to 2 meters per second. So you can't ride up a hill nearly as fast as you can ride on a flat slope. You'll see this idea more in homework 11. Thank you all for your time. If you want to stick around and ask questions, you're certainly free to do that. I will be hanging around for another 5 minutes, and then I've got to go teach another class. Let me know if you have any feedback, especially if you have feedback on like me writing on the slides here. This is a new thing that I'm trying. I've never done this before, obviously, so let me know if there's anything that I can do to make class go better. I'm going to stop the recording now.